Welcome everyone to the session on Introduction to Graph Neural Networks. And we'll get started with the session now. So this will be your reference material for today. So we'll be referring to multiple documents. The contents in the Word file. So it is there in the chat window for all of you to access. So you can just click on the chat window, or you'll have a link which you can access. So I'll be using these materials today. So yeah. So with some basics in GNN, how many of you are already familiar with graphs and things like that? Or some people are totally new to graphs? Anybody who's already familiar with graphs here, you can put yes in the chat window. Okay. Sure, there are some people who are already familiar with graphs. So today's session is going to be introduction to graph neural networks. And so what are graphs and what kind of data can be represented in the form of graphs? And what are some of the challenges when it comes for applying machine learning on graphs? And what are graph neural networks? We'll not be discussing much into the variants of graph neural networks as such, but we'll discuss about message passing, how information is represented in nodes, how information is represented in edges. These are some of the things which we'll be discussing. And then we will be moving on to outlier detection in graphs in general. So this is going to be the agenda for the session. And now let's get started. So if you see all around us, there's graphs everywhere. Social media is something which comes to our mind, but then there are multiple other use cases like recommendation systems and outlier detection. So if something goes wrong in a heavy manufacturing plant, if you want to detect any outliers in manufacturing. So there are so many use cases of graphs out there. So neural networks, applying neural networks on graph-based data has been studied, has been under research for quite long time. So it's not something which is new, but it's been studied over a period of time. But right now it has come into a proper shape. Right now there are a lot of architectures which has come out where we are able to solve real world problems. But the research has been there for quite long time. So this is a very sample example for a graph neural network. So you have multiple layers. Under each layer you have nodes. So if I press on this particular node, I can see the information which is passing from this node to multiple other nodes in each of these layers. So this is a typical representation of graph neural networks where you have multiple layers. In each layer, you have a graph representations. And and some more things about graphs is like graphs generally have something called nodes, and this is the basic structure of graphs. Graphs has got nodes, which is also called as vertex, and you also have edges which connects two nodes with each other. So this is called edges or links. And you also have something called global or master nodes, which contains a lot of metadata about the graphs, like the number of nodes, what is the longest path, and all of this. So a basic graph structure would contain all these components. One is the nodes, and there are multiple nodes here. All of this is the first component. Then you have edges which connects two nodes with each other, and you also have a master node which contains the kind of a metadata, which is like number of nodes and the longest path and all of this. And so I particularly chose this tutorial for the kind of animation it has. I'm not sure if I can pull up this animation in my slide. The animation is something which even somebody who's very new to graphs can, get an intuitive understanding using these animations. So I particularly chose this tutorial. So we've discussed the components of graphs, but graphs contains information. So if you take nodes will have some kind of an information. That information is stored in node embedding. So each node will have some kind of an information, and those information is generally called node embeddings. And edges will also be having informations, and that is called edge embeddings. And the entire master node will also have some information embedded with it. So that's called master embedding. So each and every component will of the graph has got some information which is stored in it. And you also have different variants of graphs. There are graphs which doesn't have direction. So if you take images and stuff, it's an undirected graph where one pixel and another pixel do not have any direction kind of thing. But there are graphs which have a directed edges, especially if you want to represent a group of text. Indicating one text is before another, one word is before another word. So you might have to use a directed edge for that. So there are graphs can be represented as directed and undirected edges with undirected edges. So to quickly summarize, we have learned about the different components of graphs. And we've also seen how the information can be stored in these components. And we have also seen the variants of graphs. So some of the use cases where graphs are used are, it is used in fake news detection. Traffic prediction is one of the biggest use cases for graph neural networks. Recommendation systems, where I've already used it. It's also used in molecular chemistry. It's also used in various simulation experiments as well. And mostly these images and text, representing these images and text in the form of graphs is not the research of using images with as a graph representation has been very there's a lot of research in this space in the last few years. There's quite active research in this space, both image data and text data, representing them in the form of a graphs and then applying neural networks on top of it. So this is not so common compared to other natural structures like graphs. So image is not a very naturally a graph structure. There are other use cases where you will have a natural graph structure. For example, if you take molecules, so this is a naturally a graph structure which falls into the structure of graphs. But when you take images or text, these are not so common use cases for graph-based data. But you can represent images and text in the form of graphs, and it will help you understand the finer intuition between how these components are connected with each other in images. It could be pixels. You can understand the fine grained information hidden in these data types as well. So when you take images as graphs, so how can you represent images as graphs? So image is nothing but it's basically a collection of pixels. So for each pixels, you will be representing it in the form of a nodes. And these nodes, there could be an undirected edge from one pixel to another pixel. So for example, I'm taking the cornermost pixel. There are 3 undirected edges here. Making a connection with 3 of the pixels on all the 3 sides. And so all the this is a very animated diagram. So if I hover my mouse over here, I'll be able to see the corresponding adjacency matrix, and I'll also be able to see the graph-based representation, how this particular node is represent. So all three representations are of the same image. So you can just hover over any of the image, and you'll be able to see the corresponding representation in the other 2 sides. So this is how images can be represented in the form of a graphs. So when you say representing images in the form of a graphs, one way of, capturing the connectivity is in the form of an adjacency matrix. And so you can, so if there is particular node, if there is a particular node, if there is a connection between two particular node, or this node and this node have a direct connection, then you can have a value in the adjacency matrix. So if a particular this node, second node, and this node doesn't have a direct connection, so there won't be any value between the six. So there will be a value in the adjacent matrix if two nodes are directly connected with each other. There will not be any value if the two nodes are not directly connected with each other. So the best way of representation for image as a graph data is in the form of an adjacency matrix. And you can also represent text in the form of graphs. There are a lot of use cases and pre-trained architectures now coming up in the intersection of graph neural networks and text data. For images, they are fully connected. So for text, it is little different compared to images. So here we have graphs are all around. So graph is the first word and R is the second word. So there is an edge from graphs to R. So you again, even text, it is represented in the form of an adjacency matrix. So if there is going to be a connection between two particular graphs and graphs, there's no connection, so there's no value. Graphs in R, yes, graph is following R, so there will be a value. So that's how an adjacency matrix is formed for text. So this is how text is represented in the form of a directed graph, and you can capture the information in the form of an adjacency matrix. So text and images few years back were not considered to be a common data structures for graph representation. But right now there's a lot of interesting research which is coming up. You can just Google, do a Google Scholar for graph neural networks and text-based use cases. You'll find a lot of interesting architectures which has come up in the last few years for both text data and image data. So we have discussed these two uncommon types of data types, which are which don't perfectly fit into the mold of graphical data. So now let's discuss about the typical data structure, which are naturally suited for graph-based data structure. So if you take up chemical molecules, these are a very perfect example for a graph-based data structure. So any chemical molecules, if you take, it will have an atoms and you will also have electrons. And these atoms will have, two atoms will have some kind of a binding between each other. So you can represent these atoms as nodes, and the bindings between two nodes atoms, you can represent them in the form of an edges. So if you take any 3D molecules, and all these are naturally coming into the realm of a graph-based data structure. And so this is you have multiple molecules here. Again, you have an adjacency matrix, and you can just hover over here to see how each particular node and the connections are represented in the form of an adjacency matrix. So the connections can be, it can be a single bond, or you can have a double bond and things like that, or you can have a triple bond here. A single node is connected with having 3 edges. So this is for molecules representing, chemical molecules in the form of a graph-based structure. This is a very natural use case for a graph-based data structure. And another very common, the moment you say graph-based data structure, the one use case which comes to everyone's mind is social networks. And so again, social networks is a very natural use case for representing in the form of a graph-based data structure. You take a single person, his relationship with everyone else, and all these things, you can naturally capture it in the form of a graphs. So this is a graph-based, example, sample representation of a graph-based structure for social networks. So these are people, and what is the relationship between this person and the other person. It's all captured in the form of an adjacency matrix and as a graphs. Interaction between two people and all that. So again, you have the other examples, like we just discussed about Google Scholar. You take about Google Scholar, you take any research paper. For example, I'll just go to Google Scholar. So I'm going to put so I take a paper, it has a lot of citations. So it will definitely have any research paper is going to have a lot of citations. And if I go to that paper, the citations, there are so many citations for this particular research paper. So if I click on any of these research paper, that paper in turn will have so many other citations. So this is again a use case which can be represented as graphs. So one paper can be cited in 100 different papers, and each of that 100 different papers will have different citations. So this can also be modeled in the form of a graphs. And the other use cases, so you can there are other uncommon use cases like programming codes and math equations can also be modeled as graphs. But we've discussed so far what is graph, what are the components of graphs, and some of the use cases, very natural use cases for graphs, and not so common use cases like images and text for representation in the form of a graph's data structure. And traditionally, there are what are the kind of problems, use cases we deal with graph-based data? When you take a tabular data, the kind of problems you deal with, if it's a structured tabular data, the most common problems you deal with is regression, and you also deal with classification. And what are the most common types of data? And if it's going to be unsupervised tabular data, you might deal with clustering and things like that. So for graph-based data, what are the common use cases? So in graph-based data, there are three common use cases which we will be discussing. Generally, all the use cases will be falling into three common types of problems. One is graph level prediction, another is node level prediction, and the third is an edge level prediction. So for graph level prediction, you are going to deal with prediction of a single property for the entire graph. We'll be seeing a use case to help you get an intuition about what graph level prediction means. Again, for a node level task, what we will do is for each and every node, we will be predicting some property. We'll be seeing a use case for you to get an intuition to understand what node level prediction is. And for an edge level task, we'll be predicting whether in presence of edge is not there or not. So we'll take up these three problem statements. The problems under graph will fall under these three categories: graph level prediction, edge level prediction, and node level prediction. So graph level prediction will be like the first use case. It is you're going to predict a single property for the entire graph. So we'll see an example to get an intuitive understanding of what this means. And so these are some of the common, these are chemical molecules which we have seen some time back. So some of the use cases can be if you want to find out if a molecule will bind to another molecule or not. This is actually a very famous use case. There was also a Kaggle use case. This is not just like a random thing which is given cited in the article. There was also a Kaggle use case competition which was about I'll show you that competition. If you're just interested, you can just mechanisms of prediction. So here it is about the whole thing is you're classifying drugs based on their biological properties. So here you will be just seeing if a molecule will bind with a certain molecule or not. And based on that, you will be making classifications here. So this is a graph level prediction. This use case is an example for graph level prediction. So so there are other variants which I can talk about graph level prediction. So it's not just about molecule binding with other, there are other variants you can have, whether what kind of smelling property a molecule will have or things like that. So you are trying to predict a single property for the entire graph structure, whether it will bind or not, or whether what kind of attributes it has, what kind of smell it has, and things like that. A single property for the entire graph. So this is what is graph level prediction. So it can be either sentimental analysis for text or image classification task and things like that. So these are all image classification problem, text classification problem, and all of it will fall under graph level predictions. So what about node level predictions? So node level predictions, you can take up the typical use cases of a social network. And for a single node, what are the nodes which are connected to it? And for each and every node, what are the nodes it is connected to it? And so for each and every node, you're trying to predict the property. You're trying to predict the property. What are the proximal connections for each and every node? So they have given an example of karate karate club, and there, two persons have misunderstanding between each other. After understanding the misunderstandings, who are the people who are going to remain loyal to person A as is person B? So this is an example for node level predictions. And there are again, if you take image and text, so for a classical graph structure, we have seen what node level prediction is. But for not so classical graph structure like image and text, what a node level prediction means. So for node level prediction for images will be similar to image segmentation. So if you take image segmentation, you will be for each and every pixel, you'll have to predict. For example, if you're trying to segment all the cows in an image, so each and every pixel in that image, you'll have to see if it belongs to the cow or not. So for each and every pixel in an image, you're trying to predict a property. So whether it is a foreground or part of a background, or whether it belongs to a cow or it doesn't belong to a cow. So that is an example for node level prediction. So when you take up text classification, again, predicting the parts of speech for each and every word. These are some of the examples for node level predictions for both classical graph data structure and for images and text. The third kind of problems which we have are the edge level task. So here, edge level task generally deals with whether there's going to be a presence of edge or not. So here, if there are different objects in the image, you're going to just find out, is there going to be a connection between two objects or not? Is there going to be a presence of an edge or not? This is edge level task. So, so far we have studied about the graph components. We have studied about typical examples of graph data structure, images, text. We have also seen other citations, chemical molecules and all that. And what are the most commonly, common use cases dealt with graph-based data? That we have seen it's graph level task, node level task, and edge level task. So there are some challenges in using graphs in machine learning. So what are the challenges in using graphs in machine learning? There are four main challenges which are there when it comes for graphs. First thing is permutation invariance. So this is one of the biggest challenges for graphs. See, if you take graphs, there are two graphs which will look different. So two graphs will look, visually it might look very different. But these two graphs will generate the same embeddings. But if you feed it into a neural network, it will give different outputs. So graphs are permutation invariant. Just because they have the same embeddings doesn't mean they're going to give the same input. When you feed into a neural network, they'll not exhibit the same behavior. So it means the structure can translate into, it can translate into multiple possible combinations of embedding. So graphs are permutation invariant. That is one challenges. Capturing this is going to be always a challenge. The second thing is, when you take traditional machine learning, most of the algorithms work under the concept of Euclidean distance. That is distance between the target and the actual prediction. It all depends on the concept of Euclidean distance. But when it comes for graphs, the whole concept of Euclidean distance doesn't work that way. And so this is again one of the challenges when you apply graphs in machine learning. So it is, one is it's non-Euclidean in nature, it's permutation invariant, and the other difficulty when it comes for graphs is its size. So what happens when you have huge millions of nodes and huge millions of edges between them? So graphs we generally represent in the form of an adjacency matrix. And when it comes for huge millions of rows and huge millions of this, then we will be, creating a lot of sparse adjacency matrix and representing for every node and for every edge. If you are representing that in the form of an adjacent, so many adjacent matrices, then that it also leads to size and space complexity. It might not be size and space inefficient. There will not be sufficient space for you to store all that information when it comes for a huge graph. The graph is like has got million nodes and million edges, then there could be problems of storing all these adjacency matrix for each and every node and each and every edge. So size and space complexity is there. It is permutation invariant, and it is also non-Euclidean in nature. The whole concept of traditional Euclidean space in graph doesn't work that well. It works really well when it comes up when you take the context of machine learning, traditional machine learning, but it doesn't work that well for a graph-based data structure. So these are some of the common problems, some of the challenges when it comes for applying machine learning techniques on graph-based data. But there are still a lot of researchers which are coming out in this intersection. So far we have learned about what are graphs, what are the use cases of graph-based data structures, and the natural ones and the ones which are not so common. What are the main problem types in graphs? And then we have also seen some of the challenges for applying machine learning on graph-based data. Finally, we are onto the main topic of graph neural networks. So to understand graph neural networks, we need to understand certain concepts really well. So in graph neural networks, we will be using graphs. So that's why we understood the components of graphs. So a graph has three components, which we have already discussed. One is the node and the edges, which connects two nodes. And you also have a global context, which contains all the information about the thing, number of nodes, longest edge, and all that. And one thing about GNN is you can GNN applies a lot of transformations on these three components, nodes, edges, and the global context. But while applying these transformation, it does not change any of the symmetries. That is, you cannot apply transformation on a graph, and then you cannot change the node the edges which are connect. You cannot change the connection between two nodes and things like that. So you can GNN has to while applying transformation, GNN has to keep the underlying symmetry intact. So it has to apply transformations without changing the underlying symmetry. That is one of the main principles GNN has to follow. So that is very important. And GNN is a huge concept. So there are a lot of concepts like pooling, message passing, and a lot of these things are there. How do you get the edge level embeddings? How do you get the node level embeddings? What happens when nodes have values? Because in real world, we don't have any perfect graph data structures or any perfect data set for that matter. So sometimes we might have the values for nodes and sometimes we may not have the values for edges. Sometimes we'll have the values for edges and sometimes we'll not have the values for nodes. So real world data set is very, very unpredictable. So now we'll be discussing the use case of simple GNN. Then we'll be discussing the what happens when certain values of nodes are present, but then edge value information is not there. What happens when edge value information is there and nodes are not there? How will we handle these situations? And then so to handle these situations, we'll be looking at a concept called pooling. But this pooling, you can only do it in the final layer. So if you want to pass information in the GNN layer itself, we'll be dealing with another concept called GNNs, and we'll also be having learning about global representations and edge level representations and all that. So these are the topics which we are going to see up next. To represent the most simple GNN, what happens with simple GNN is for each and every node, you are passing it through a multi-layer perceptron. And after you pass through a multi-layer perceptron, you're learning, getting an embedding. And then you are for each and every node, you're learning a new embedding by passing each and every node into a multi-layer perceptron. So this is a very, very simple GNN. This is what happens in a very simple GNN. Not just the node, for each and every edge, you pass it through a multi-layer perceptron and you will be learning the edge embedding. And the same thing, you will be passing the global context vector through a multi-layer perceptron, and you will be finding the global context vector embedding for the entire graph. So this is what a simple graph neural network looks like. So for each and every component in the graph, we pass it through a multi-layer perceptron and we learn the embedding for each and every component. This is what happens in the simplest graph neural networks. So, but in the most simple graph neural networks, what happens is there is no, we are not going to update any connectivity and things like that. We are just going to, the update process will not happen. What this update process is something which we will learn little later when we come to message passing. So in the most simplest graph neural networks, all you're going to do is you're going to take each component of the graph and pass it through a multi-layered perceptron, and you're going to learn the embedding for each and every component. And so now this is perfect when everything is good. We have the node level information, we have the edge level information, we can pass it through an MLP, learn the embeddings and all that. But in real world, the data is not like that. Sometimes you will have node level information, sometimes you will not have, you will have only edge level, no node level. Or sometimes you will have only node level, you not have edge level. So the real world data is unpredictable. So we will be looking into special cases where only node level data is there, but edge level data is not there. When edge level data is there, node level data is not there. How do you get the data in these cases? So in these cases, we do something called pooling to find out the data which is not available. So what is this process of pooling information? So that is what we're going to see up next. So what happens in pooling is, for example, if you don't have node, take the first case where you don't have node level information, but you have all the edge level information. What you do is in pooling, you actually aggregate all the values. You take, for example, we'll take this first node. So for this node, there are two edges which are passing on to the node. So we'll take this embedding of these two edges, and then we'll first take the embeddings of two edges, and then we'll do an aggregation of it. Aggregation can be anything, some minimum or max or something, any form of aggregation. And for example, we take these two embeddings, the edges which are going to the first node. There are two edges which are going to the first node. So we'll take the embeddings of these two, we'll do a sum, and then we'll assign that sum value. After doing a sum of these two embeddings, we'll assign that value to this node. So this is how, when a node level value is not present and the edge level values are present, we can actually find the node level value. using this whole process called pooling. You can do the same thing for edges as well. You take an edge, there are two nodes, but take the case where edge value is not present, but the node values are present. So what you'll do, this particular edge has got two nodes. So take the values of these two nodes, do an aggregation. Aggregation can be max, min, anything. To the basic form of aggregation you take, for example, we'll do a sum. We'll just add those two embeddings and then we'll assign it to that edge. So this is a special case. No, this is a very common case where sometimes you'll have node level embedding, sometimes you'll not have edge. So based using this process of pooling, we can actually find the values of whatever embedding which is missing. We can actually predict those values. So this is the whole concept of pooling. So in pooling, we do two things. First, you gather all the embeddings, and then the second operation is aggregation. So this is for edge embeddings. When edges are present, and you will have to predict the values for this diagram is when values of edges are present, but you have to predict the values of nodes. And you have the case where the values of nodes are present and you have to predict the values of edges. So these are two cases. This can be achieved using the process called pooling. So pooling, we do two things. First, what we do is we take the information, we gather the information, and the second process is we do aggregation. So the next thing is there is another concept called message passing in graphs. So you can do pooling only at the final layer. What if you want to pass messages between graphs and nodes, between nodes and edges, between nodes and edges in the GNN layer? So you have a GNN layer, then you have a final classification layer generally. So in the GNN layer, if you want to send message from nodes to graphs, what do you do? There is another concept called message passing. So what is the difference between message passing and pooling is, first, in pooling or message passing also, you will be gathering all the information and you will be doing an aggregation on it. But in addition, there's one more step you will do. You will also do an update function. You will also call an update transformation function on the aggregated value. So this is one extra step which you will be doing in message passing. So these are so message passing generally, if you want to share exchange information between nodes or edges within the GNN layer, then you can go for message passing. So I'll show you where. So you have the graph neural networks, then you will also have a classification layers based on it. So we have other cases like learning edge level representations. So when you learn edge level representations, what kind of ordering you have to use to learn edge level? See, when you're doing update, how do you update? So do you first update? We have three components in graphs. So it is node, edges, and we also have the global context vectors. So which particular component we should start updating first? Because every component we pass it through a multi-layered perceptron and we do an updation. So which component should we start the updating first? So that is also one consideration which you have to take into. It's a design choice which you need to make. And there is also another concept called global representations. The whole concept of global representations here is there is something called global context vector, which is nothing but which contains kind of metadata about the number of nodes, what is the longest path, and all these details. So what happens when you want to learn the information between, you want to send information between two nodes which are very, very far from each other? So in this case, there could be some inefficiencies. You may not be able to, no matter how much you try, how much of message passing and how much of pooling and how much of message passing you do. If two nodes are very, very far from each other, then there could be a possibility that message passing may not be efficiently done. So how to handle this case? in that case, you can go, in that case, specific case, this whole concept of global context vector makes sense, because you can ensure every node, it can act as a master node, and it can, get connected to every node. So it will contain information about every other node. So it can act as a bridge connecting two nodes which are very far from each other as well. So that is about global representation. These are some of the basic concepts of graph neural networks. So there are different variants of graph neural networks. So each of these variants differs in how you do the aggregation and how you do the updation. So message passing, if you take the first step, is aggregation, and the second step is updation. So based on how this aggregation and updation process happens and what kind of data structure you deal with, there are different variants of graph neural networks. You have graph attention networks, you have graph convolutional neural networks. So there are multiple other variants of graph neural networks which are present based on the kind of how you do the aggregation and updation process. So this is about the basics of graph neural networks. We'll look at a specific use case of outlier detection using graph neural networks. So graph neural networks are very used very commonly in graph-based outlier detection. So we'll look at that now. So if you take why graph neural networks are very successful whenever you take any tabular data problem, and if you want to perform outlier detection, graph neural networks are much more successful than the traditional non-graph based methods. And so we'll look at some of the use cases where outlier detection is used. You can take any network failure just because of some kind of an anomaly which has occurred, or some kind of outlier has entered your network, or any network intrusion, there's some odd behavior which has come up, or any fraudulent behavior in banking systems. These are all some of the examples for outlier detection. And all of these examples, graph-based outlier detections are very successful in all of these use cases, especially in tabular data. Graph-based neural networks works really well. So one of the use cases is about Twitter bot. I think Twitter bot is right now in everybody's mind because of Elon Musk. And if you take this particular use case, you will find the first page. If you take standalone as a single Twitter page, it is very difficult to find anything suspicious about the account on the face of it. Everything might look very perfect. But when you can identify bots is when you analyze a group of accounts which are connected with each other. That time it is very easier to identify a bot account, because each and every account shares some common properties. So when you analyze the Twitter accounts which are connected with each other in a social network, because each and every Twitter account will have a lot of similarities. When you try to do a mapping, you will be able to find the anomaly, sort the bot accounts very easily. This applies to any tabular data problem as well. In granular data problems, graph-based outlier detections are quite successful as well. So there are some concepts in graph-based outlier detection as well. One is structured outliers and the other is contextual outliers. If you take structured outliers, so the first you see here is a structured outlier. So this is densely connected with each other. All the nodes are densely connected with each other. So this is an example for a structured outlier. So the second category is called contextual outliers. So here, if you take the only anomalies is because this particular red color node has a very different properties compared to its surrounding nodes, and that's why it's an anomaly. So that is contextual outliers. So these are some of the different types of outliers which are available in real world use cases, which we come across in real world use cases. So GNN based, graph based outlier detection, how does it work? So if you take what some of the if you take for GNN based outlier detection, we have to use GNN autoencoders, which is we will be taking a GNN and then we will be mapping into an autoencoder. So the GNN will act as both encoder and decoder. So you take any single image, for example, if you want to find an anomalies in an image or whatever it is. So the image, you are feeding the autoencoder both the proper images and the images which has anomalies. It will actually take an image, it will try to read it and then encode it and then try to reconstruct it. Autoencoders, basically what they do is they try to consume an input and they try to encode it and then they try to reconstruct it. So in reconstruction, if it is a proper image without any anomalies, the reconstruction error will be very less. And for data with anomalies, the reconstruction error is going to be very high. So this is how graph-based node outlier detection works. So for graph-based node outlier detection, the kind of architecture which we use is graph autoencoders, where you will have an encoder and a decoder, and you will be trying to encode the graph data, input data, and then trying to reconstruct it. And in the reconstruction phase, when you have a lot of error, that's how you will spot an anomaly or outlier detection, or you'll detect an outliers. So some of the common challenges when you take up graph-based outlier detection is, graph-based outlier detection does not work well with small graphs. But if you take large graphs, it works really well. So that is one problem. The second problem is whenever you take unsupervised problem, there's a lot of tuning of hyperparameters which has to be done. And the whole process of tuning hyperparameters for an unsupervised problem is not that easy. So that's also one challenge. And most of the graph-based outlier detection methods, they work really well in a synthetic outlier context. But when it is a natural outlier, which is very difficult to spot, they don't work that really well. And so these are some of the challenges when it comes for graph-based outlier detection methods. And there is also one kind of a library there's a library called PyCord, which is developed based on PyTorch and PyTorch geometric, which is a library which is integrated very well with the ML workbench of Tiger Graph. And with just 5 lines of code, you can actually detect anomalies. And this, the whole thing is very easy to implement as well. You're just importing a package, which is a dominant here, and you're giving the hyperparameters. So here, this PyCord library, you are importing the dominant outlier constructor here, and it has some hyperparameters like number of layers you want to have in your GNN and number of epochs. You can give your hyperparameters, and then you have to feed your data, and then you will be able to see the outlier scores. It's just 5 lines of code, which is integrated well with the Tiger Graph's ML workbench, and you can detect outliers easily with just 5 lines of code. This is just one library. There are several other libraries out there as well. You can also try out PyTorch geometric, and yeah. So this is about the session. We've come to the end of the session. We started with introduction to graphs, and then we saw the components of graphs, different types of graph representations like the directed graph and the undirected graph. And we also saw what are the different use cases for graphs. And we also saw what are the major types of problems which is handled in graphs. Then we discussed about the graph neural networks, and we discussed about some of the concepts of graph neural networks, and starting with how we write, what are the concepts involved in simple GNN, then what is pooling, when we do pooling, and what is message passing, and why do we require a global vector representation. And we also saw one specific use case of outlier detection using graphs, graph-based outlier detections. And we also saw some of the different types of outliers which are there. And how does graph-based outlier detection happens, like, the general concept of graph autoencoders. And then we discussed about the Pygod library. So this is the end of the session. We've got some 8 minutes left. So if there are any questions, we'll just handle that.
Thank you, Usha. It does look like we have some questions in the chat. If we want to start there, maybe I don't know, maybe answer the ones that you can. I think that would be beneficial.
Yeah, so for the outlier detection, is GNN more compute intensive than methods like DB scan? So it depends on GNN. If you're going to use autoencoder, it may not be that compute intensive. But DB scan, it depends on the use case as well, how the data, how the nodes are connected with each other, and the size of the node. Is it a small data or it's a big data? So if it's going to be a very big data sets, I think graph neural networks generally works well. But anything deep learning, you require good compute power. Based on the data size, you definitely require good compute power. But more than discussing compute intensive, first, is DB scan really going to be that effective when you take up a graph-based data with huge volumes of nodes and millions of nodes and millions of edges? A method like DB scan, it won't be that effective in the first place. Graph-based outlier detection is much more effective. Compute intensity, anything deep learning requires a lot of compute power, and graph-based deep learning definitely requires much more compute power. So in terms of effectiveness, yes, graph-based neural networks are better when it comes for outlier detection, but compute intensive, yes, they are. Does graph-based neural networks provides better accuracy, other benefits over traditional neural networks like TensorFlow or PyTorch? See, you can actually use graph-based neural networks using TensorFlow. There's something called TensorFlow GNN, if you're not aware. So the first one of the PPTs which I've shared is about TensorFlow GNN. So graph-based graph neural networks is a concept. It's an abstraction which can be implemented in any framework. So you can implement the whole thing in TensorFlow as well. There's something called TensorFlow GNN, Keras API as well. So this whole presentation I have added it here. So you can look at this PPT, and the appropriate links to the official documentation and TensorFlow website will also be there, which you can look at it as well. So PyTorch will also have, PyTorch has got PyTorch geometric. So the whole concept of graph-based neural networks can be implemented in any framework, can be implemented in PyTorch or TensorFlow. What are the different loss functions in GNN? Loss functions in GNN will be similar to what kind of use case you are going to deal with. For example, if you're going to deal with a classification problems, and GNN classification problem, you might, if it's a multi-class classification, you might be having categorical cross entropy or binary cross entropy. So it depends on in GNN what kind of problem statement you're dealing with. And it's going to be the similar, if it's a classification problem, the same loss metrics which are applicable for classification will be working here as well. I think the specific reason for choosing Tiger Graph over Neo4j or Dynamic DB, Neptune is actually an experiment tracking thing. It's not, I don't think Neptune is an experiment tracking software. Neptune.ai is what you're referring to, right? It's an experiment tracking software. So the difference between graph databases, I think you will have a session, upcoming session where they'll be discussing what are the advantages of in future. Watch out for all the sessions. There's one session which is coming up, Tiger Graph 101, where they will be discussing in detail about what are the advantages of Tiger Graph over the other databases. That is a session I think you should watch out for. Oh, Amazon Neptune. Okay. So yeah, I think you have a session which is coming up, Tiger Graph 101. So that I think they're going to have a longer discussion on that. So here it's just the session is about basic introduction of Tiger Graph. So I'll not comment on that. So the document link is here.